Hi there, if you follow my channel for some time, you know that I've collected a number of LCR meters, mostly vintage and some needing repair. This causes a problem: how to check if these meters are still accurate and, if necessary, calibrate them. One needs precision capacitors and inductors, which are very expensive, and if you buy slightly cheaper used ones, you don't know again if you can trust them. Another way would be to use good but not precision capacitors and inductors and measure them with a good and trusted LCR meter. That way, they would become your own reference standards to verify and calibrate LCR meters. In short, to verify my LCR meters, I need verified reference standards, and to create these reference standards, I need a verified LCR meter. Rinse and repeat. One of my UK viewers, Dave, offered a solution to break this circle. He loaned me his ET4410 LCR meter. The ET4410 is a very nice bit of kit. As with many professional LCR meters, it uses the 4-wire method and comes with Kelvin probes that connect to these 4 BNC connectors. Dave's ET4410 is part of a whole family of LCR meters, which only differ in how many test frequency they support and whether the frequency and test voltage is in fixed steps or continuously variable. The rest of the specs are all the same. The range and resolution for L, C and R are impressive and way more than what I have to offer as test objects. I also did not test the R mode, as I have enough ways of testing R, but I did test ESR for capacitors. The basic accuracy is stated as 0.1%, but as with most LCR meters, the actual accuracy depends on a number of things, and in the ET4410 case, this is a complex topic, and since I want to use it as a reference, I need to explain this dry topic a bit more, but hopefully as concise as possible. Looking for more info on accuracy, the ET4410 manual contains this complex graph. It marks 4 nested areas of accuracy. In the middle we have the 0.1% accuracy area. Somewhat further outside is the area of 0.2%, followed by the 0.4% area and then the 2% area. Anything outside is basically undefined in terms of accuracy. To read the diagram, let's say we want to measure a 1 nanofarad capacitor. Its line starts in the 2% area at frequencies between 10 and 100 Hz. Right at 100 Hz it enters the 0.4% area, and following this further, slightly above 1 kHz we enter the 0.2% area. Just before 10 kHz we briefly enter the 0.1% area, but at a little above 10 kHz we are briefly back in 0.2% territory, and at well before 100 kHz we are back all the way to 2%. The lesson here is that for best accuracy a 1 nanofarad capacitor should be measured at 10 kHz. Sadly, the manual is silent whether the division markings in the diagram are meant to be logarithmic or linear. I assume they are meant to be logarithmic, which makes a big difference for extrapolating values that are not marked. For example, in the logarithmic scale, 3 nanofarad is about halfway between 1 nanofarad and 10 nanofarad, but in linear scale it would be much closer to 1 nanofarad. The frequency axis has the same uncertainty. If squinting at difficult graphs isn't your thing, the manual offers an algorithmic way of determining accuracy. Unfortunately, even more complicated, because this reveals that accuracy depends on much more than just the measurement frequency. For capacitance, inductance, impedance and resistance, the accuracy is always 0.1%, which is then multiplied with some factors. The manual contains tables for the frequency depending values of Cmax, Cmin, Lmax and so on. I don't show them here. There is this additional term with Ks, Kv and Kf. Ks depends on the selected measurement speed. Kf is again depending on the selected frequency, and Kv depends on the selected measurement voltage. In each case, the term that is multiplied with the base accuracy is 1 plus Ks plus Kv plus Kf. The values of these is always between 0 and a positive number. If any of these is greater than 0, the result makes the accuracy worse. It follows that for best accuracy one must select those conditions where Ks, Kv and Kf are all 0, because in that case the whole term becomes 1 and multiplying with 1 makes the accuracy determined by the other parameters at least not worse. It is easy to see that this means one should select slow measurement mode because that makes Ks 0. A frequency between 100 Hz and 1 kHz makes Kf 0. Unfortunately, in some cases higher frequencies are needed for other reasons. At least 10 kHz incurs a moderate penalty, but 40 to 100 K makes Kf 4, meaning the accuracy gets at least 5 times worse compared to 1 kHz. The measurement voltage should be set to 1000 millivolt or 1 volt, because that makes Kv 0. Interestingly, it gets worse on either side of this, with 100 millivolt incurring a value of 9, meaning the accuracy gets at least 10 times worse compared to 1 volt. My guess is that 1 volt is what the factory used to calibrate the ET4410, and so it's best to stick with it. So far so good, but there is one more thing that kind of ruins this whole algorithmic approach. You see there that the accuracy for C depends on knowing the dissipation factor dx of the capacitor being measured, but how would you ever know that without measuring it? Same for inductance accuracy depending on the quality factor Qx, which is the reciprocal of dx. Is one supposed to measure first d and q and plug these into these equations? But how accurate is measurement of d? There's a formula for that, and you guessed it, it depends on dx. And q measurement has the same circular dependency. A high D or a low Q means a bad capacitor or inductor, and that will likely ruin the accuracy of any measurement, but I'm honestly struggling to understand what EaseTester is trying to do here. To be able to use the algorithmic approach at all, I assume perfect capacitors with 0 as dissipation factor and inductors having an infinite quality factor, because in this case the pesky dx and qx terms disappear. With these caveats, here's my crude model. You type in the capacitance in nanofarad in the yellow box and get the light yellow accuracy values for 4 different frequencies. For inductance, it's the green box in millihenry and light green accuracy values. The factors for Kv and Ks are set to the best values of 1 volt and slow measurement. Under these circumstances, the spreadsheet predicts that a 1 nanofarad cap would have best accuracy at 0.17% when measured at 10 kHz. If you remember the results from staring at the complicated diagram, we had transitioning from 2% to 0.4% at 100 Hz, getting to 0.2% at slightly above 1 kHz, entering 0.1% around 10 kHz, and we're back at 2% at 100 kHz. While these results confirm 10 kHz as the best frequency and better than 0.2% as best accuracy, the other values at the less accurate low and high ends are a little away from the accuracy diagram. My guess is that the diagram was simplified a little, especially when accuracy gets worse. Using my spreadsheet, I did my own diagram using the formula with the caveats explained for a number of capacitors and inductors. Here is the one for capacitors. It's quite interesting and hopefully easier to understand than the one in the manual. On the bottom we have the 4 frequencies I tested. On the vertical is the predicted accuracy in percent. Both axes are in logarithmic scale because of the huge range they cover. If we start with small caps, 10 picofarad to 1 nanofarad, their accuracy improves as we get to higher frequencies. That said, it's clear that you will never be able to measure 10 picofarad or lower caps with 1% or better accuracy. Note that I simply connected the predictions with lines under the assumption that the behavior doesn't abruptly change in between frequencies. Accuracy for caps of 1 nanofarad to 100 nanofarad kind of dip at the best accuracy point, which is at 10K, and shifts to 1K for the larger values. Larger caps are measured most accurately at the lowest frequencies of 100 Hz, which is kind of expected. But you should notice that even at the lowest frequencies, there is no chance to measure anything larger than 100 microfarad with at least 1% accuracy. And for even larger caps, the best accuracy gets worse very quickly. 6.3% is the best possible accuracy for a 1000 microfarad cap. My inductance chart shows a very similar picture. Small inductances are best measured at high frequencies and larger ones at low frequencies. Well, that's kind of understood, but you can see that the 1 microhenry has a close to 100% error as the best accuracy, and 10 microhenry measurements cannot be more accurate than 10%. Even 100 microhenry measurements can only be accurate to 1.3%. Also, for both capacitance and inductance, these are the best case predicted accuracies, assuming capacitors with zero dissipation and inductors with infinite quality factor. Real components are of course always worse, which drags down the measurement accuracy. Just to be clear, I'm not dissing the ET4410. Measuring capacitance and inductance is complex, literally, but I'm not going to dive into the math. Borrowing this page from an IET primer on LCR measurements, you have a choice of treating your capacitors as ideal capacitors in series with a resistor or as an ideal capacitor with a resistor in parallel. Same story for inductance. And these models are actually simplified because, for example, every real capacitor has both a series and a parallel resistance, and possibly some inductive component as well. In practice, the influence of these extra components can usually be ignored, but they may influence precision instruments. All LCR meters have similar accuracy limitations, whether they are openly stated or not. At least with the ET4410, you kind of know what accuracy to expect depending on the settings. And there are a lot of these. The ET4410 allows you to use either the serial or parallel model. You can select frequencies in step from 100 Hz to 100 kHz, select the measurement voltage, the measurement speed, and apply a selectable DC bias. This gives a whole choice of parameters to select and to get wrong. There is a two-stage auto mode in the ET4410. The first, where it tries to figure out by itself if you are measuring a capacitor, inductor or resistor, and then in stage 2 whether to use parallel or serial models. To be honest, I found the auto mode often got it wrong, showing for example resistance instead of inductance, and I much prefer selecting the measurement mode myself. The ET4410 has a lot of functions that I have not explored. These are lists of measurements and set up tolerances, thresholds to sort components into classes. Much more common is selecting the frequency of the sine wave used for testing in 16 discrete steps. The range is from 100 Hz to 100 kHz. In my test, I only used the 4 most commonly used ones for LCR measurements, namely 100 Hz, 1 kHz, 10 kHz, and 100 kHz. You can select a different measurement speed, but as discussed, slow gives the best accuracy, and that's what I used. Slow is still pretty fast, and honestly I can't think why one would choose any other speed. The amplitude of the sine wave can be selected in steps between 0.1 volts to 2 volts. Again, the best accuracy is at 1 volt, so I left it at this value. There is a special button for electrolytic capacitors that just presets some parameters which you can actually also set by hand. The key one is that it enables a DC bias voltage of 1.5 volts. I tried measuring electrolytic caps with or without bias, and there was very little difference. But if you measure caps that have been unused for a long time, it probably makes a difference. Another selection you can do manually is switching between serial and parallel mode. This is available for any component, not just electrolytic caps. Parallel mode is indicated by the P in the function name. Serial mode shows the letter S. The second set of measurement readouts, which are again available for all components, not just electrolytic caps, are the inductive or capacitive reactance X, the dissipation factor D, its reciprocal, the quality factor Q, the phase angle theta, and finally the equivalent series resistance ESR. Of note, these selections are not available in auto mode, another reason why I generally did not use it. Okay, my plan is to measure a couple of capacitors and inductors with the ET4410 and make them reference standards. Here are the capacitors ranging from 10 picofarad to 4700 microfarad. Some, like this one, are actually references already. This is a 10 nanofarad cap with 0.9% tolerance from an old LCR meter. I bought that one used on eBay. On the other side of the spectrum is this standard 4700 microfarad cap from Rubicon. I picked it in the hope it will keep its parameters for some time. I marked it with yellow so I won't use it for anything else. You may also remember from an earlier video that I have this capacitance decayed from 10 nanofarad to 11.1 microfarad in 10 nanofarad increments. Later I decided to leave this decay out of this video as there is just too much data otherwise. For brevity, I'm also not showing the individual measurements, only the results and some special cases. But for inductors I will use this decade because frankly I don't have that many inductors lying around. This decade goes from 1 millihenry to 1.11 Henry in 1 millihenry steps. But in line with the content of my standard reference capacitors in the box, I will only use some of the possible settings of the decay to limit the amount of data. The tolerance of these inductances is 5%. I left the ET4410 to warm up for an hour and then use the CAL function to get the best accuracy. To do that, you first leave the two Kelvin clamps so they don't touch each other and press the CAL button for a couple of seconds. The meter shows CAL open and a countdown. It takes quite some time to complete, so this video is accelerated. When completed, it shows OK. Next, make sure the two Kelvin clamps are connected to each other and then press CAL again for a few seconds. The meter now shows CAL short and another countdown. Once that finishes, the meter is now calibrated. After CAL, the remaining residual capacitance with nothing connected is just -1 picofarad. This is at 100 Hz, but as you have seen, small caps need higher frequencies, and indeed at 1 kHz we get more digits of resolution. Instead of 1 picofarad, it now shows 0.732 picofarad. As we have also seen, the meter can't really measure 1 picofarad or less with any decent accuracy anyway, so it's not surprising that increasing the frequency to 100 kHz does not improve this result any further. During my measurements, I found that sometimes the ET4410 is not able to settle on a value, like here, where I measure the 10 nanofarad standard at 100 Hz. I suspect that sometimes the problem is caused because the selected frequency causes a huge error, but in this case the predicted accuracy at 100 Hz is 0.26%, which is nearly as good as the best case of 0.12% at 1 kHz. I found that this problem can be fixed by turning auto range off and lock the range. If you do that at the right moment, that's all that's needed. Otherwise you may have to go to a better frequency first, where the meter is stable, lock the range and then go back. You can see that the 1 kHz frequency gives a slightly different result. And 10 kHz again, a small difference. And the same happens for 100 kHz. In this case, the best predicted accuracy for 10 nanofarad would be at 1 kHz, which is the measurement frequency one should select for this cap. Here I'm measuring a 2 nanofarad cap at 100 kHz. The best frequency for 0.16% accuracy is actually 10 kHz, and at 100 kHz it has dropped to already 0.57%, but I show this to demonstrate another feature. If faced with a value where the last digit is unstable, you can press average, and the ET4410 is calculating the running average and shows that at the bottom of the display. Keep this running until it doesn't change anymore and use that value instead. Sadly, average is only available for the primary displayed value, so capacitance in this case, D or any other secondary readout, cannot be averaged this way. I previously mentioned that there was this residual capacitance of -1 picofarad at 100 Hz after CAL. The ET4410 allows to null that. It now shows that it will subtract 1 picofarad from whatever it's measured. Unfortunately, this display replaces the line for the secondary readout, for example D. Anyway, if I now connect my sample of a 100 picofarad cap, I get about 102 picofarad. If I now remove null, the value drops to 101 and the secondary measurement of D reappears. Apart from losing the secondary measurement, this is all fine, but be aware of the following. I am measuring 10 picofarad at 100 kHz and get about 9.6 picofarad. Pressing null and the meter takes the momentary value and now subtract 9.623 from all measurements. So far so good, but watch what happens with the average. The value is 9.622, not close to 0 as you would expect. So average always uses the raw measured value and not the one corrected by the null offset. Here, this is very obvious, but with small offsets it's quite difficult to spot, and I had to repeat quite a number of measurements because I had relied on average using the corrected value. Here I am measuring an inductance of 330 millihenry at 10 kHz and get about 340 millihenry. Please ignore the average readout, I forgot to reset that from a previous measurement. When I increase the frequency to 100 kHz, I get plain nonsense. Although the predicted accuracy of 1.54% at 100 kHz is not that bad. Switching from serial to parallel has no effect. I think this is a problem of my decade, which for 330 millihenry at 100 kHz has turned to become a capacitor. Apart from the inductance decade, I have this little box I made some time ago with a selection of small inductances. Such a box with banana sockets is actually not easy to measure with Kelvin probes. You either have to open it to apply the probes directly at the component leads or at dummy plugs, which can then be properly clamped with Kelvin probes. So after all this, here are the results. Capacitors on top, inductors on the bottom. I marked in green where the accuracy should be 0.5% or better. Yellow shows at least 1% or better, and red marks the rest. I recorded data for all 4 frequencies to be able to compare data with other LCR meters that may have different best frequencies. I also recorded a lot more data, such as D and Q, but all this will be useful in future videos when I compare other LCR meters with this dataset. For now, maybe it's interesting to see how the capacitance and ESR values for electrolytic caps drop with higher frequencies. It is clearly plain nonsense to measure electrolytics at 10 or 100 kHz, resulting for example in 4700 microfarads to show as 47 microfarads. But what can you expect if the predicted accuracy is just 147,000%? Let's finalize this video with a look inside. Dave graciously gave me permission, and here is how the ET4410 looks inside. The construction uses a main PCB that contains the measuring part and the power supply. There's a small PCB at the back that handles the USB serial port and remote control port. The back of the PCB does not contain any components. A separate front plate PCB handles the buttons and display. Overall, it looks well put together. The transformer markings. 2 primary 110 volt windings, which is common in a lot of Chinese equipment because of the 220 volts mains voltage used in China. In the UK the voltage is nominally 230 volts, but usually closer to 240 or more. This means this transformer is actually slightly overdriven, but I do like that the device uses a linear power supply. The DC operating voltages are stabilized by the usual 3-pin voltage regulators on generous heat sinks, and they had no issue with a slightly higher input voltage. 5-volt rails seem to be used for most of the unit, but the 4th regulator is an adjustable LM337. All very standard and easily repairable if needed. The ET4410 has 2 of these 32-bit ARM Cortex kernel-based N32G455 microcontrollers on board, one on the main PCB and the other on the display board. They include the usual digital I/O, but also have 4 12-bit high-speed ADCs, 4 op-amps with programmable gain, and 2 12-bit DACs. This explains that nearly all other chips on the PCB are just high-speed analog multiplexer and demultiplexers like those two. And they are just 2 10-turn trim pots, and it's clear that they are not meant to be changed. The input protection of the ET4410 seems pretty good. Apart from lots of clamping diodes, there's one gas discharge tube for each of the B and C inputs. I believe the 075 indicates they fire at voltages of 75 volts or more. While exploring the inside, I noticed this capacitor that seemed to be missing a bit. It's a 470 nanofarad plus minus 5% capacitor rated for 250 volts and therefore much more likely used for decoupling or protection than a reference for measurement. I don't think the capacitor exploded in an overload event, as this would leave more marks and debris. Also, the capacitor measures still fine. It looks more as if the coating simply cracked and fell off when the capacitor was roughly handled during assembly. I guess it happened already in the factory because I could not find any bits left in the housing. The problem is of course that with the capacitor open to the environment, especially humidity, it may change value over time or fail completely. So Dave and I decided to replace it with a new one of the same type, which is what I just did here. Well, the ET4410 still works after the operation, and after letting it warm up for an hour and then running CAL, I measured my 10 nanofarad reference cap, which came with the same results, so accuracy has not been degraded. Well, this is it for this video. The next LCR video will be on the vintage ET4410 LCR data bridge, where I will use my new reference capacitors and inductors and compare the results with the ET4410. If you enjoy my videos, don't forget to like and subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.